Hello YouTube. In this video I'm going to talk about graphing functions. And what I'm going to show you here is one of my favorite functions. This has the shape of a small round hill. The height is 1 and it's centered on 0. The left and right side is symmetrical, and one of the main advantages of studying this function is that it's very simple. 1 over x squared plus 1. Let's make a little table of values and see why this has the shape of a round hill. Starting in the column of x at -3, we're going to go up 1 unit at a time up to +3. And in the next column, we compute x squared. So -3 squared is 9, -2 squared is 4, -1 squared is 1. At 0, it's 0, and then all the positive numbers are the same as the negative numbers. So, the shape of this is a parabola. I think almost everybody learns the shape of this curve in high school. And plotting these points, starting at the origin, it goes through the point 0, 0 as the minimum. The next step, we'll add 1 to this. So adding 1 to each number just means that the curve is moved up 1 unit. So it still has the same shape, except now the minimum point is at a height of 1, at the point 0, 1. And it's still a parabola, still symmetrical on the left and right. In the next step, we divide 1 by this number, x squared plus 1. So the bigger the number is, the smaller the result is. When x squared plus 1 is equal to 10, then 1 over 10 is 0.1. So at -3 and +3, the height is 0.1. At plus and minus 2, the height is 0.2. At plus and minus 1, it's 0.5. And at 0, the height is 1. So, for this first explanation of drawing a function, I made out this table, but in general we'd like to avoid this process and just think about this graphically. And that is by understanding the shape of the x squared part as a parabola, then raising it up 1, x squared plus 1, and then inverting it. The process of inverting it leaves the 1 unchanged. So in the bottom picture, the dashed line is x squared plus 1, and the solid line is 1 over x squared plus 1. You can see at the point 0, 1 that it's unchanged, and on both sides it gets to be a smaller and smaller number on each side. Next, we're going to move this function over 4 units to the right. And we do this by replacing x with x minus 4. So in this case, we can also make a table just to show that the first step, changing x to x minus 4, converts the numbers between 1 and 7 into -3 and +3. And after that, it's just the same process. We square that number, then we add 1 to it, and then we get the inverse of that number. So we get the same shape of a small round hill, except now it's centered at 4. Let's look at this graphically. The first step, y minus 4, is a diagonal line, going from the lower left to the upper right at 45 degrees. And it's the same as the diagonal line passing through the origin, which is y equals x. It's just lowered 4 units. And in the case of the 45-degree diagonal line, lowering it a certain number of units is equivalent to moving it to the right 4 units. So at the point 4, the diagonal line passes through the axis and the value of y is equal to 0. The next step in processing this equation is to square that number. At 4 it's 0, and away from 4, it goes upwards in the shape of a parabola like we saw before. So x minus 4 squared looks just the same as x squared, except it's moved 4 units to the right. And this is true of any function. Any function that we have an x and replace it by some x minus a, where a is the distance that we want to move it, it will look the same, just moved those a units to the right. In the next step, we just add 1 to it. So this bottom parabola is y is equal to x minus 4 squared plus 1. And now we have the parabola with its minimum point 4 units to the right of the origin and 1 unit above the x-axis. So the point 4, 1 is the minimum point on this. And the original function 1 over x minus 4 squared plus 1 is dividing 1 by this number. So when this number is 1, it stays unchanged. So the top of the hill has a value of 1, and it gets smaller on each side. Next thing I'd like to show you is adding 2 functions together. And for our example here, we'll use the 2 functions that we've already talked about. The small round hill centered on 0, and the small round hill centered on 4. So the way that we add up 2 functions is that we take the y value of either function and add them together. And these functions are particularly easy to understand because they have interesting features within a constrained boundary. In other words, near 0, the function is doing its most interesting behavior, and far from 0, it's almost exactly 0. So, as a first approximation, we can just ignore the one function because it's close to 0, where the other function has its features. So the first part of this equation has the feature of a small round hill centered at 0, and the second part is the same thing centered at 4. When we add them together, we get 2 small round hills centered at 0 and 4. The second example, where we subtract one function from another. In this case, the first hill is positive, so it goes upwards, and the second hill is negative, so it goes downwards. And in the third example, instead of 1 over x squared plus 1, we have 3 over x squared plus 1. That makes it 3 times as high. So we have a round hill of a height of 3, centered at 0, plus a small hill at the height of 1. Okay. The next function I'd like to show you is to replace x squared by x to the 10th power. Now this might look a little bit intimidating at first, to use a high power that in most schools they are not teaching people how to graph functions with these higher powers. But it's not too bad when you get used to it. We'll first think about what raising something to the 10th power does to a few particular values. 0 stays 0, and 1 stays 1. Negative 1 becomes positive 1, and after that it rapidly gets big. So at the point 2 and negative 2, it's 2 to the 10th power, which is about 1024. Also, another feature of this function is that the bottom is very flat. So that at the point 0.5, or 1 over 2 to the 10th power, is the same as 1 over 2 to the 10th power, 1 divided by 1024, which is about 1/1000th, 0.001. So this function is pretty flat in the center, and it stays near 0 until we get up to about 0.8 or 0.9. Then it goes up through the point 1, 1 and the point negative 1, 1, and then rapidly becomes a large number outside of that region. When we add 1 to this function, x to the 10th power plus 1, it has the same shape. Every point is just moved up 1 unit. So we can describe the shape of this as being almost exactly 1 between negative 1 and positive 1. Actually, at negative 1 and positive 1, the value is 2. But between about negative 0.8 and positive 0.8, it will be very close to 1. Now, the third step, we're going to divide 1 by this. So in the region between negative 1 and 1, where the bottom part of this function is almost exactly 1, dividing 1 by it, it'll stay 1. It'll just be slightly smaller than 1. And outside of this region, where x to the 10th power plus 1 becomes very large, then 1 divided by this becomes very small and approaches 0. So what we have is a flat-topped mesa function that has fairly sharp shoulders. And this is both interesting and helpful because it's easier to draw and to use in various ways, as I'll show you. Here we've moved the function 1 unit to the right. And we do this by replacing x with x minus 1. So 1 divided by x minus 1 to the 10th power plus 1. It has the same shape of this flat-topped, relatively sharp-shouldered table function that drops off at the point 0 and 2. Right at 0 and 2, the height is 0.5. But between about 1.9 and 2.1, it does most of the dropping. Underneath it, I just drew as a reminder the function 1 over x to the 10th plus 1 before we moved it. You can see that they're the same shape. And let's think about what happens when we add them together. And I call this the Olympic function for obvious reasons. The values between 0 and 1 is close to 2. The values between negative 1 and 0 is close to 1, and between 1 and 2 is close to 1. Now the reason for this is that between 0 and 1, both of the component functions have a height of 1, so when we add them together we get 2. In the region from negative 1 to 0, the height of the second function is 1, but the height of the first function is 0. So the height there is only 1. And it's just the opposite for the right-hand shoulder between 1 and 2. The height of the first function is nearly 1, and the height of the second function is near 0. So the net result is that we have this function that goes up at negative 1 and goes up again 1 unit at 0. Then it comes down 1 unit at 1, and it comes down 1 more unit at 2. Now, hopefully everybody is familiar already with the sine function. I'll make another video introducing it for those that are not. But the sine function is a smooth wave that starts at 0, goes up to a maximum at a value of 90 degrees, and comes back to 0 at pi, about 3.14. Then it goes down to -1 and comes back up to 0 at 2 pi. In order to make this easier to draw and work with, I'm often using the function sine of pi times x. Now the effect of pi times x is just to make it easier to draw so that it's going through a half cycle in every unit. So this function will come back down to 0 at the point 1, where the original sine function came back to 0 at the point pi. And then it comes back to 0 the second time at 2, where the original function came back to 0 at 2 pi. Next, instead of x, let's plug in the flat-topped table function that goes from 0 up to +1 at -1, and then falls from +1 down to 0 at 1. When we feed this into the sine function, it means that we get two bumps near -1 and +1. If we had used 2 pi in there, we would have one full cycle taking place near -1, and the same cycle in reverse order at +1. So the function goes from 0 up to +1, down to -1, and then comes back to 0, near -1. Then near +1, it's just the opposite order. First goes down to -1, up to +1, and then back to 0. And in the next example, we've just moved this over one unit to the right by replacing x with x minus 1, so that it does the little full period of the sine function near 0 instead of near -1. And it does the opposite order of the sine function near 2 instead of at 1. But the shape is the same. Now this top function I just put in for a reminder of the equation of the flat-top Mesa function. And we're going to feed this into sine 2 pi. So where this goes from 0 up to +1, near -1, it'll make the sine function go through a full cycle, going up to +1, down to -1, and back to 0. And then it does it again near 0. So it goes up to +1, down to -1, and back to 0 at 0. And it does the reverse at 1 and at 2, where the top function is falling first from 2 down to 1 at x equals 1, and then falling from 1 down to 0 at x equals 2. This next function underneath it is adding to the two sine functions that are shifted over. Now this will visually look about the same as the one above it. They're not equal mathematically, but the difference is not apparent, especially for a hand-drawn diagram. One other thing I'd like to say about functions that are visually similar in a hand-drawn diagram, but significantly different if you look at some of the values, is the original function that I showed you, 1 over x squared plus 1, and the function e to the minus x squared. which you'll soon see in statistics. And the function e to the minus x squared falls off to 0 much more rapidly. At the point x equals 3 in the first function, it's still 1/10. At the point x equals 3 in the second function, e to the minus x squared, it's e to the minus 9th power, which is a very, very small number. We can estimate it by saying that e squared, 2.7 squared, is not too different from 10. So if we have e to the minus 8th, it will be about 1/10,000th. That is 1/10 to the 4th power, which is a 10,000th. And e to the minus 9 will be about 1/3 of that, very close to 0.